And what I'm going to be talking about is essentially how and when to use dot products and what the benefits of doing different techniques are. So first off, let's just discuss really what is a dot product. Well, let's lay it out first. We have our M vector, which I'm just going to call M for no reason, just M. So we have mxi plus my j hat plus mz k hat. Okay? Just laying out what portions of the vector contribute to which portions or which direction, which component, you know? That way you can see exactly what's happening here. Great. So, when someone says, hey, do this, m dot n, what that essentially is saying is almost like, what do they have in common? That's probably not the most accurate way of saying it, but essentially what you're doing is you're bringing one vector and you're seeing what portion of that vector could be a component of the other vector. So case in point would be like if we were just trying to find out which portion of the xyz or the xy of this vector right here, if we did the dot product of this vector f and let's just say the x-axis, then the resultant would be this, the component right here. So this would be f dot, and then I'm just going to say like the direction of x. So basically it's a way for them to show essentially what portion of that vector is a part of the other vector. That's kind of like how I like to describe it. So anyway, what is m dot n? M dot n. You're going to find this stuff really easy. Essentially what this is you just multiply all of the same component variables for both vectors. So mx times nx plus my times ny plus mz times nz. And you just add them all up. And that is essentially, that's going to be the magnitude of it. And it's just going to have the direction. You have to find out which one you're trying to find, but I mean, it'll have a direction of whatever vector you picked. But the resultant is going to be a scalar number right now, because obviously we forgot, well, we didn't forget, but we just didn't put in a direction. So, I just wanted to notice that since this is scalar, remember we did have a scalar technique for cross products, and similarly there is a scalar technique for dot products, and often enough you'd actually want to use that more. But I'll just show you. It's going to be m times n, and these are the magnitudes of each cosine. And that equals the same thing as m dot n. It's the same thing. So you can use the scalar technique at any point and get the same result. So essentially a lot of people are sitting there going, okay, so now that we know how to come up with, we know around about what direction it's going to be in. We know that based off of our little drawing here. We know that our result's going to be scalar, so we just have to pay attention to which direction it's going to be in. And also we know this other scalar technique, which we might be able to utilize in maybe some simple situations, but we always have the vectorial approach if it gets too complex. So why do we need to know this? Well, I mean, a lot of people use this to find, they'll add a dot product in there to find out what part of the torsion is actually being applied to an axis. So remember when we had like let me think of an example here. Just think of a door, really. I mean, if you had a door, and you know that the door can only rotate on this axis, that y-axis, and everything's all fine and dandy if you push perpendicular, but I mean, if you push downward and left, what you're going to find is that while it does cause a rotation, a moment or a rotation about maybe this point 0 or 0.0, but in the reality for the axes it makes no difference, and that's how we utilize this dot product to only show us what affects the axes. So let's see, let's just start off here. I'm going to try and use this little technique, okay? So let's just say that this axis right here, this door axis, is going to be our A axis, just for argument's sake, okay? And while we probably understand what it will be, I'm just going to give it some numbers. AYJ hat plus AZK hat, right? Okay, and then also, if we say that we applied this force, let's say we applied it smack dab in the middle here, I'm going to give it a few coordinates, okay? This is going to be 3 feet from here to here, and from here I'm just going to give it 3 feet as well. Don't judge me on how accurate that is, because it's not. And let's just pretend like this is going down and touching this point at 30 degrees or 60 degrees. Okay? So what I want to do, and we probably won't even put numbers in here, I actually just feel like showing you what it's going to look like. Remember when we were trying to find the moment, say about O, what we would put is moment of O will equal, then we would go I, J, K, and then you would have your R length, which in this case is going to be whatever your R length is. It will be R will equal 3, let's see, 3J plus 3K. That's what our R will be, because Z will come out this direction, right? If this is the X, or if this is X direction, so there we are. So what our R would be is 0, 3, 3. Okay? Then you have to have your force, and your force, I mean, you could just, let's just say that you had a direction. I'm not going to give it, but it'll be F of X, F of Y, and F of Z, okay? And we would use this technique, and this would find the moment about O. What if it was about the axes? Now what they want you to do is say, okay, well then you have to do the dot product of this resultant. So you could run it through this way, or you could incorporate it, which I'm going to show you how to do. Essentially all you do is you put your axes on the top rather than I, J, and K. So what's our axes? I'm just going to put AX, AY, AZ. Okay? Then you'll realize that these all, while I am putting them in general form, you realize that this would simplify your situation, and so basically to do the axes, all you have to do is put the axes coordinates right here. That'll save you a lot of time. And this is actually the same thing as saying, well, you have your axes that you're interested in, and dot product of our cross product. It's the same thing. So anyway, let me just put in a couple labels here. A is the axes of rotation. Okay, then you have your R, which is, I'm going to just call it the moment arm. And then you have your F, which is your, essentially your applied force, right? Okay. So, basically, I want you to just kind of look at this in a more general form right now, and basically, if we were trying to find the component of a vector, so for vector v, what component would we do if we want, or what axes, or A, would we do to find the component of the x component, right? Well, A would have to be I, because then you do the dot product of I, and the only things with I would show up and give a value. More on this in the next video. I'll give some examples. Good one. Have a good one.